Hey folks, this is Heath. We're not covering any new material today. This is just a review on chapter 14. Um, some of the stuff that we've been doing so far. Let me give you a heads up though to what's going on here. There will be no class on Wednesday. Um, Enjoy the extra day. Spend a little extra time going over chapter 14 if you have any. I will be watching email and getting back to that, but we won't be holding any classes at all for this class anyway that day. Friday, we're going to start chapter 13. We have 4 sections left. 4 sections, but I'm going to spread it out over 5 days. And so that will be Friday of this week, and then Monday, Wednesday, Friday of the next week, and then Monday of the week after that. Um, and then that's November the 14th. And then um, Wednesday the 16th. I think I've got my dates wrong. Let me see what that date actually is. No, this is the November the 16th. November the 18th, which is a Wednesday, will be a review for test 3. And then test 3 would normally be on that Friday, which is the 20th. But I know a lot of you are going to be trying to pack and move out and get ready. That Friday's going to be busy for people, and so I'm going to open the test on the Thursday. So November 19th will be test 3, but I'll leave it open through the 20th. Um, but the goal is so that you can get test 3 out of the way before you go home for Thanksgiving. Enjoy the break with your family. Um, Not have to worry about taking a test, you know, when classes resume. Um, After Thanksgiving, we don't meet face to face at all anymore. We will be, you know, spread out all over the country, and but we have a couple of weeks after Thanksgiving, and we'll use that time to review for the final. Um, and the goal at that point to be to do as well as we possibly can on the final. Um, One of the differences between the final and the midterms is that the finals are not open notes, and so we have to, you know, get a little bit more robust about how do we know how do we do this material without having the notes in front of us, and so that's what we're going to be focusing on after the Thanksgiving break is taking the material that we understand and make it a little bit more solid. Okay? So let's look at over what we've done in chapter 14. We did 4 sections so far. The 14.5, which was a section on the multivariable chain rule. This is the idea that if we have a function that depends on x and y, and then x and y in turn depend on some variable t, then there are 2 different ways that t changes the value of z. T influences x, which influences z, but t also influences y, which influences z. And so we calculate partial derivatives along each arrow, the derivative of z with respect to x times the derivative of x with respect to t, and the x's cancel, And this gives me a partial derivative of z with respect to t. But then we do the same thing with over y. The derivative of z with respect to y is this arrow times the derivative of y with respect to t, which is this arrow, and that's dz dt. Also, the dy's cancel. And again, this is a partial derivative, but if we add them together, then we get the derivative dz dt. We can generalize this to any number of variables. We can do much more complicated diagrams in this, but the principle remains the same. Find out all the paths that go from this variable to this variable, multiply the partial derivatives along the paths, and then add all the partial results together. Okay? Section 14.6, we introduced the notion of the gradient vector. This is the partial derivative of f with respect to x and the partial derivative with respect to y written in the form of a vector. The rate of change in the direction parallel to another vector is called the directional derivative. This is the notation for a directional derivative. The derivative of the function f in the direction of the vector v. And the formula for that partial directional derivative is a dot product of the gradient with the direction vector divided by the magnitude of the direction vector. The gradient vector is always orthogonal to the level curve at the same point, and the gradient vector always indicates the direction in which the function increases most rapidly. Then 14.7, we talked about local and absolute extrema. To identify critical points, we look for places where the gradient vector is either 0 or undefined. The critical point is a saddle point if the torsion product outweighs the concavity product. If this is greater than this, or in other words, if this determinant is negative. It would be negative if, when we multiply these together, those are the two concavity values, minus the two torsion values, the answer is negative. If the critical point is not a saddle point, then either concavity value represents the concavity at the critical point, but you can use fxx for that. And then that determines whether the critical point is a local maximum or a local minimum. Then if we want to find absolute extrema on a bounded region, we have to test the critical points that are on the region, along with the critical points along the edges, along with any corners of the region. And that sometimes results in a very large number of points to test. If we want to find the extreme values of a function subject to some constraint, we look to satisfy this pair of equations where the gradient vector of f and the gradient vector of the constraint are pointing in the same direction, which means the only difference is a scalar, a multiplier, that takes one vector to the other. And then the constraint itself has to be satisfied. If we have to do this subject to two constraints, then we add the multipliers by the two constraints together, and that has to equal to the gradient vector for f. That's the only difference. Okay? So let's go through a couple of problems here, and hope this helps. So let's look at this. Is this a true or false statement? There is a function that has continuous second partial derivatives for which the partial derivative for x is x plus y squared, and the partial derivative for y is x minus y squared. Now you could try working your way backwards, taking an antiderivative. If this is the derivative with respect to x, then this term would have to go to x squared over 2, and this term would have to go to xy squared. And then try to figure out a way to make this work with that. But the other thing that we would notice is that if this is fx, then fxy is 2y. But fyx would just be 1. And these aren't equal. And that violates Clairaut's theorem. You can have a function where fxy and fyx are different, but that requires that the function has to have an infinite number of discontinuities, and what we're told is that the second partial derivatives are continuous here. And so not only is the original function continuous, but the derivative and the second derivatives are continuous, and that can't happen. And so this is false. This can't happen. All right, let's try this one. The directional derivative in the direction of the k vector is equal to the partial derivative with respect to z. So let's talk about what this is. This is the gradient vector dot product with the k vector over the magnitude of the k vector. The gradient vector is the partial derivative with respect to x, the partial derivative with respect to y, the partial derivative with respect to z. The k vector is the vector 0, 0, 1, and the magnitude of the k vector is 1. And then when we work out this dot product, I get 0 times fx plus 0 times fy plus 1 times fz over 1, and that actually is fz. And so this is a true statement. We just had to work out what the definition of the directional derivative was in order to show that this was true. All right. Let's keep going. If f has a local minimum at the point and f is differentiable at AB, then the gradient vector is equal to 0. That is true almost by definition. They have a local minimum, include the places where the gradient vector is equal to 0, or the places where the gradient vector is undefined. But if the gradient vector is undefined, then the function is not differentiable at AB. And since we're told that f is differentiable at AB, then the gradient vector won't be undefined, and so the gradient vector has to be 0. That's the possibility that's left. And so this is a true statement. If the function has 2 local maximums, then the function must have at least 1 local minimum. This works in 2 dimensions. In single variable calculus, if I had a function with a local maximum and another local maximum, then it would have to have a local minimum in between if f of x, so this is in single variable calculus, if x is continuous, then the function would have to reach a minimum between the 2 maximums. But in single variable calculus, we could also have a vertical asymptote, and we could have a function that has a local maximum and then goes down to a vertical asymptote, and then on the other side does the same thing, has a local maximum and then goes down to a vertical asymptote. So if x is continuous, then this statement would be true. But if we don't require the function be continuous, we could not have a minimum because the functions could go down to infinity, and have a break in there. The same thing can happen in 3 dimensions as well. We could have a function that has a local maximum on the left side of an axis, and then goes down to an asymptote, and then has another maximum over here, and heads down to infinity, and there's this whole plane in between where that separates the two pieces. And so this statement is false because fxy may be discontinuous. Okay. In fact, even if it's continuous, this is going to test my drawing skills. We could have, instead of a minimum in between them, we could have a saddle point in between them. We could have a function that looks like this in one direction, but in the other direction is always heading downwards. And so this is a local maximum because it's heading downwards in every direction. This is a local maximum because it heads down every direction. But in between, it's only a minimum in this direction, and it's still a maximum in this direction. Has a saddle point in between instead of a local minimum. So number 4 is a statement that would have been true in single variable calculus if the function was continuous. In multivariable calculus, it can be false in two ways. It can be false if the function is discontinuous and we have just two different shapes on either to the side that has local maximums and doesn't reach a critical point in between because of its discontinuity. Or we can have a continuous shape that has two maximums but a saddle point in between them instead of a minimum. Okay? All right, let's move on. Let's look at some of these multiple choice questions. We have this function here, x squared plus kxy plus y squared, where k is a constant. Which of these statements is correct? So let's look at the derivatives. The derivative in the x direction is 2x plus ky, and the derivative in the y direction is kx plus 2y. We would like to see when these are equal to 0 because those will be our critical points. And, well, something interesting happens here. If we try solving one of these equations, for example, this one here, we get 2y equals to negative kx. And so y is equal to negative kx over 2. And so fx is 2x plus k times negative kx over 2, or 2x plus negative k squared over 2 times x. I could factor out an x from this and get 2 minus k squared over 2. And that gives me two answers here. X equals 0. And if x is equal to 0, then y will also equal to 0. Because y is negative kx over 2. And that's a critical point. But the other possibility is that 2 minus k squared over 2 is equal to 0. If 2 minus k squared over 2 is 0, then 2 is equal to k squared over 2. So if I bring the 2 over here, 4 is equal to k squared, and so k is equal to plus or minus 2. And something interesting happens in those cases also. Um, if k is plus or minus 2, this becomes a perfect square, and this factors in a way that it wouldn't factor if k was not equal to 2. Um, so then we're testing also then for local minimums and local saddle points. Not local saddle points. And let's figure out what's going on here. So um, these were the places where we had critical points. Okay. The second derivative with respect to x is 2, fxy is k, fyx is also k, and fyy is equal to 2. And so the determinant of 2k, k2 is 4 minus k squared. So which is bigger, the concavity products or the torsion products? Well, it depends on the value of k. If k is less than 2, or if the absolute value of k is less than 2, then 4 minus k2 will be positive. And if the absolute value of k is bigger than 2, then the 4 minus k squared is going to be negative. So this can be positive or negative. And so neither of these choices work. This choice says it doesn't matter, for every value of k we have a local minimum. And this one says for every value of k we have a saddle point. Whether or not we have a saddle point depends on what k is, whether this is positive or negative. Okay? But if the absolute value of k is greater than 2, this is going to be negative, which means we have a saddle point at our critical points and not a local minimum. And so this is correct. It's correct because the function won't have a local minimum because it has a saddle point instead. This is wrong. If the absolute value of k is less than 2, then 4 minus k squared is going to be positive, and then we will not have a saddle point. We will have a local minimum. And so D doesn't work. All right. Let's keep going. Consider these two statements. At the point 2,1, the function grows most rapidly in this direction. At point 2,1, the directional derivative in this direction is 0. All right, so let's start with this function here. The derivative in the x direction is y squared, and the derivative in the y direction is 2xy. And we're looking at the point 2,1. Well, at the point 2,1, fx is equal to 1 squared, which is 1. And fy is equal to 2 times 2 times 1, which is equal to 4. And so the gradient vector is equal to 1, 4, which is the same thing as I plus 4j. Well, the gradient vector is always the direction in which the function grows most rapidly. And so 1 is definitely true. So what about number 2? Is 2 also true? Well, we also know that gradient vector of f is perpendicular to level curves. And it is true that the vector 1, 4 is perpendicular to the vector negative 4, 1 because their dot product is equal to 0. And so this is the direction of a level curve. and the function is constant along a level curve, and the derivative of a constant is 0, and so this is also true. But if you didn't remember that this was a level curve, you could also use the formula that the direction, if I call this vector v, the directional derivative of v is the gradient vector of f dot product with v over the magnitude of v. And the dot product of these two vectors is 0. The magnitude is square root of 17. That's okay. And you get 0. And so we could actually work out the formula for the directional derivative, and you would get 0. Or you could know the fact that since this vector is perpendicular to the gradient, it has to be a level curve. Both of these are true. All right, let's keep going. Let's look at this function here. The partial derivative with respect to x, in this case, is e to the x squared y times 2xy. And the partial derivative with respect to y is e to the x squared y times x squared. This will be 0 if either x or y is 0. F of x equals 0 if either x or y equals 0. But f sub y is 0 only if x equals 0. And so f of x is equal to 0 if either of these is 0. But f sub y is 0 only along here. But since the question is asking where are both of them equal to 0, that only happens along the y-axis. And so the answer is A. All right. So let's look at number 4. If you downloaded this early in the morning, if you downloaded the PDF, there's a typo in this point. I've corrected it now. The absolute minimum of this function over the line segment containing these 2 points. So that's containing 2, 0 and 2, 2. That line segment right there. We want to find the absolute minimum along this line segment. Well, this is the line segment x equals 2. And along x equals 2, my function is 4 plus 4y squared minus 4y. And the derivative of that function is 8y minus 4. If we set that equal to 0, we get 8y equals to 4 and y equals to 1/2. And so the point where x equals 2 and y equals to 1/2 is a point that we have to check. But we also have to check the 2 endpoints. And the endpoints are 2, 0 and 2, 2. So this was a critical point, and this was an endpoint, and this was an endpoint. Okay? So let's see if we can make this work. When x is 2 and y is equal to 1/2, this is 4 plus 1 is 5, minus 2 is 3. At this endpoint, when x is 2 and y is 0, 2 squared is 4, 4 plus 0 is still 4. 4 minus 0 is still 4. And at this endpoint, when x is 2 and y is 2, 4 plus 16 is 20. 20 minus 8 is 12. And the question is asking for the absolute minimum. The absolute minimum right there is equal to 3. All right. All right, let's keep going. Let's try some free response questions. Use Lagrange multipliers to find the maximum and minimum values for this function subject to this constraint. So the gradient vector of f is the derivative with respect to x is 2xy, and the gradient vector with respect to y is x squared. The gradient vector for my constraint is 2x, 2y. And we're looking for points where the gradient vector of f is a multiple of the gradient vector of g, or that's saying that 2xy is equal to lambda times 2x, and x squared is lambda times 2y. Those are the two equations we want to work with. Well, the top equation tells me that lambda equals y. Lambda is equal to y. The other possibility, the other way that lambda might not equal y, would be is if x was equal to 0, because if x is 0, then lambda can be anything, or x equals 0. Well, if x is 0, then because we get 0 on this side, then y will also have to be 0. The other possibility is at lambda is equal to y, and then what we have here is x squared is equal to lambda times 2y, so that would be 2y squared. And if I substitute that into the constraint, then I have 2y squared plus y squared is equal to 1. So 3y squared is equal to 1. And so y is equal to plus or minus the square root of a third. And then x then turns out to be plus or minus the square root of 2/3. Okay? So we have 4 critical points, or 5 critical points. Um, 0, 0, positive root 1/3, positive root 2/3, the other way around, 2/3 and 1/3. Root 2/3 and negative root 1/3, negative root 2/3, positive root 1/3, and negative root 2/3 and negative root 1/3. And my function is x squared y. Well, in this case, that's easy to compute. That's 0. X squared y is going to be 2/3 times the square root of 1/3. So that's 2 over 3 root 3. This will be negative 2 over 3 root 3. This will also be negative 2 over 3 root 3. No, it would be positive 2 because the x is being squared. And here we'll still get a negative because this is a squared term times a negative. So that will be negative 2 over 3 root 3. So the maximum value is 2 over 3 root 3, and that happens in two places. And the minimum value is negative 2 over 3 root 3. And that also happens at two places. All right, let's keep it on. Let's find the local extrema and the saddle points for this function here. So the partial derivatives are 3x squared minus 6y and negative 6x plus 24y cubed, y squared, sorry. And we want to set these equal to 0. All right. So in the top equation, I can take out a three, and I get x squared minus 2y is equal to 0. And so get x squared is equal to 2y. And so y is equal to 1/2 x squared. All right. So if I substitute that into this equation, I get negative 6x plus 24 times 1/4 times x to the 4th equals 0. I'm taking this term and squaring it. So the 1/2 gets squared and becomes 1/4, and the x squared gets squared becomes x to the 4th. And so this is negative 6x plus 6x to the 4th equals 0. Well, if I take out an x, this becomes, actually take out a negative 6x. This becomes 1 minus x cubed is equal to 0. And so either x is equal to 0 or 1 minus x cubed is equal to 0, which is saying that x cubed is equal to 1, and so x is equal to 1. If x is equal to 0, y is also equal to 0 because 1/2 x squared is equal to y. And so 0, 0 is a critical point. And if x is equal to 1, 1/2 times 1 squared is 1/2, and so 1/2 is equal to y. And so these are my two critical points. 0, 0, and 1, 1/2. All right. So then let's test them to see what we have. So let's look at the second derivatives. The second derivatives, fxx, are 6x minus, just 6x, sorry. And fxy is negative 6. Fyx is also negative 6. And fyy is equal to 48y. So at 0, 0, which is our first critical point, we have the matrix 0, negative 6, negative 6, 0. And the determinant of that matrix is negative 36. That's definitely a saddle point because we have a negative determinant. So 0, 0 is a saddle point. All right, so let's look at the other point at 1, 1/2. then we're taking the determinant of 6 times 1, which is 6, negative 6, negative 6, and then this is 48 times 1/2, which is 24. But that determinant turns out to be 144 minus 36 is 108. That is definitely not a saddle point. And the concavity is positive, so that's concave up, and concave up means that our critical point is a minimum. And so 1/1/2 is a local minimum. Okay. Let's keep going. Let's find the maximum rate of change in this function, x squared y plus square root of y at the point 2, 1. So the partial derivative with respect to x is 2xy, and the partial derivative with respect to y is x squared plus 1/2 y to the negative 1/2. At the point 2, 1, this is 2 times 2 times 1, which is 4. And this is 2 squared plus 1/2 times 1 to the negative 1/2, which is just 1. And that's 4.5. And so the gradient vector is 4 and 4.5. Okay? That's the direction. That's the answer to the second question now. To find the actual rate of change in that direction, this would be the directional derivative in the direction of the gradient vector of the function, which is equal to the gradient vector dot with the gradient vector over the magnitude of the gradient vector. And that turns out to be just the same thing as the magnitude of the gradient vector, which is the square root of 4 squared plus 4.5 squared. So 4.5 squared is 16 plus twice the terms is 20.25. So square root of 16 plus 20.25 equals the square root of 36.25. And that's got to be the maximum rate of change. Square root of 36.25. Okay? All right. Let's find the points on the hyperboloid x squared plus 4y squared minus z squared equals 4, where the tangent plane is parallel to 2x plus 2y plus z equals 5. So let's call this function f. The gradient vector to the hyperboloid is 2x, 8y, negative 2z. And the normal vector to the plane is 2, 2, and 1. And these vectors have to point in the same direction, which means that 2x, 8y, and negative 2z is some multiple of 2, 2, and 1. Well, that says that 2x is equal to 2 lambda, which is the same thing as saying that lambda is equal to x, or x is equal to lambda. 8y is equal to 2 lambda. And that's the same thing as saying that y is equal to 4 lambda. And negative 2z is equal to 1 lambda. And so z is equal to negative 1/2 lambda. And up here I've got the fraction wrong. It should be 1/4 lambda, not 4 lambda. If we substitute those into the function f, we get lambda squared plus 4 times 1/4 lambda squared minus negative 1/2 lambda squared equals to 4. This is lambda squared plus 4 times 1/4 squared is 4 over 16, which is 1/4 lambda squared. Negative 1/2 squared is positive 1/4 lambda squared. And these terms cancel. And so lambda squared is equal to 4. And so lambda is equal to plus or minus 2. Well, when lambda is equal to 2, we have the point x equals lambda, y equals lambda over 4, which is 1/2, and z equals negative 1/2 lambda. And when lambda is equal to negative 2, we get all of these except for their negatives. And so there are 2 points on the hyperboloid, and here they are. All right, last one. Suppose that u is this function here, depending on x and y and z, where x depends on t and y depends on t and z depends on t. Compute du dt. Well, along the path from u to x to t, that's saying that du dt can be made up of du dx and dx dt. Du dx is the derivative of this function with respect to x. That's 2xy cubed. And then dx dt is the derivative of this function with respect to t. That's just 2. And that answer is 4xy cubed. All right. Then let's look at du dy and dy dt. All right. Du dy is 3x squared y squared. Dy dt is cosine t. And so there's not a lot we can do with that. That's just 3x squared y squared cosine t. And then finally, du dz, dz dt is the derivative of this function with respect to z is 4z to the third. And the derivative of z with respect to t is 2t. We multiply those together, we get 8z cubed t. And if we add all of these together, we get the answer we want, 4xy cubed plus 3x squared y squared cosine of t plus 8z cubed t. All right. I hope this helped. Y'all have a good couple of days. I'll see you again on Friday. Take care.